here are the last two questions that I'm going to do. This first one, impulse and momentum. I think we concentrated more on the oblique collisions, but I wanted to do one of these with you. I think we did it very briefly in one lesson, and I spent a long time actually doing it an alternative way and then showed you. And here's the impulse momentum triangle, which is a much easier way to do it. So we've got 3 points. A batsman strikes a ball at mass 0.25. So the ball is initially coming in at this angle here, or coming in what we see to be horizontally. Of course, all line the horizontal plane, it just means it's on a flat cricket pitch. So the horizontal plane, the plane is flat. But then it talks about immediately before the ball is struck, the ball is moving along the horizontal line AB. So it's then referring to this horizontal as well. With speed 30 meters per second, immediately after being struck, the ball then moves in. Whoa, come on, rub off. There we go. The ball then moves in this direction here. So this is after being struck. Now, for that to happen, you know that there needs to be an oomph kind of giving it, making that change in velocity, giving the change in direction. And that oomph, of course, is what we call the impulse. And you can just kind of see, just intuitively, but just your extensive knowledge of playing cricket strokes, that the impulse is going to be going, it's going to be going somewhere in that direction. Now, because impulse is a mass times by a velocity, it's essentially, well, it is a vector product. But it means that we can consider these 3 different vectors on the same diagram if I don't write it as 30, if I write it as m multiplied by 30. And similarly there, I'm going to write that as 40 multiplied by m. And I think we know what the mass is. Yeah, the mass is equal to 0.25. And you know that that initial mv, which is 0.25 times by 30, so 30 over 4, together with the impulse, so the impulse I along there, those 2 vectors together is going to give rise to this velocity here. So that one there, let's go over that in blue again. This one here. And of course, I can see that that is pretty much going in that direction there. So MV, which is, that's going to be 40 times by a quarter, so that one's going to be 10, is the resultant of adding your 30 over 4, that one there, along with your I going up there. And then you've established what we call a impulse momentum triangle. Impulse momentum triangle. And I think when I first did this with you, we did it looking at components and so forth, but much easier to do it like this. And you're only ever going to have 3 things there. You're going to have the initial speed, the impulse, and then the velocity afterwards. So you're always going to be able to draw a triangle. We need to find the magnitude of the impulse. So if we know one of those angles, we should be able to find I. And of course we do. Let's just get rid of this, because I know that my red direction is there. And I know that my blue direction velocity is there, and we know that the angle in between them is 60 degrees. So of course I've got exactly that same angle here. And sorry, I can speed, you can do your trigonometry, can't you? Now all we need to do is use cosine rule on that. So I squared is equal to 10 squared plus 30 over 4 squared, 7.5 squared, minus 2 times 10 times 7.5 times by cos 60. That goes. So that is 81.25. So I is the square root of 81.25, so it's just over 9, isn't it? 9.01 Newton seconds. Okay, so fine, I think. The size of the angle that the direction of this impulse makes with the original direction of motion AB. Okay, so we've obviously got this angle here. And I can easily find that angle there. Let's call that theta. So I'll have that sine theta over 10 is equal to sine 60 over I. And I was 9.01. If we work that out, we get that theta is equal to 73.9. Okay, and you might think, yeah, that's fair enough. But the direction of the impulse makes with the original direction of the motion AB. So let's just have a think about this. And I think going back to this here is the most obvious way to see it. My impulse is going in this direction. Let's be consistent with the colours though. So my impulse is going in this direction here. That is my impulse. That is my direction AB. This is the angle here that we need. Okay, and in general, whenever you're asked for the angle in between two vectors, they either both need to be heading towards each other, or they both need to be going apart from that coinciding point. So you can see the problem with my triangle here. I've got one heading towards the point and one moving away from the point, so that's going to give you the incorrect angle. And of course it would be a little bit annoying, wouldn't it? It would lose 1 mark of this question, I'm afraid. So we would then have to say, but the angle required is 180 minus 73.9, 106.1. So just always make sure you find the correct angle. But as a question, hopefully you'll agree that's not too tricky. Circular motion, we haven't done this for a while. So I know you suffered a little bit because this was a topic that was rushed a little bit to try and get it all done before lockdown 1. And then I kind of picked up you guys halfway through, and much as it was a pleasure to do, it was all a little bit, oh, not quite sure, have they done this, have they not done this? And then there was a especially evil question, wasn't there, on the paper that you did when we came back in September, I think it was. So let's try a vertical circular motion question, but possibly one that isn't quite as nasty as the one you did in the September assessment. Vertical circular motion. Every single time you do the same 2 things. I know you can get some quite complicated problems and you can have many forces, but essentially it's the 2 things every time. Firstly, you find an expression for V squared using energies, using conservation of energies. It's the same every single time. And then we find some force. It could be tension, it could be normal reaction using F equals MA. But using F equals MA with the 2 different variations, V squared over R if you've got velocity, or omega squared R if you've got angular velocity. And a lot of the time, it's this first one. It's this first one because in the first part, using the energies, it's the V squared that automatically pops out. Okay, so these 2 processes, however complex your situation is, if it's a vertical circle, this is what we do. Okay, so let's look in particular at this question here. Oh, these formulas, by the way, they are given to you, but they're given you in, well, that one is expressed as theta dot squared. You are given that as v squared over r. So they're on the formula sheet. Okay, so you look at this. Okay, all right, it's a little bit abstract, but you don't care because you know how to do it because it's using energies. I guess if you're looking at that, you're thinking, okay, well, it's an expression for v squared essentially, and you know that there's a v squared that appears in a half mv squared for kinetic energy. It is specifically talking about speed at the highest path, the speed at the lowest path. So it makes complete sense to think about the total energy at A, total energy, kinetic energy, plus gravitational potential energy. Now we're just about to start a period of work that talks about elastic energy, but for the moment, you do sometimes get circular motion questions that also involve elastic energy, but they are of the trickier variety. Aren't many of those about. Half mv squared plus mg times by, all right, so where is our zero height? I think it makes sense to put the zero level at the bottom. Mark that on your diagram. Okay, it's going to help you if it's a particularly tricky question. It will certainly help anyone marking your work. So at A, the radius is A, so of course that total height there is 2A. And then the energy at B. So kinetic energy plus gravitational potential energy is equal to kinetic energy, a half m, its velocity is 7v. Of course, there's no potential energy because we're at the bottom. So that will be 49 over 2 mv squared. And now we can say, using the conservation of energy, okay, and you know, I would encourage you very much to write it down. You'll be doing some questions that got lots and lots of processes. Write down, again, it's also good to signpost for the examiner, but also for your understanding. So energy before, which is half mv squared plus 2 mga. I say energy before. Energy at the top, energy at A, is equal to the energy at B, which is the 49 over 2 mv squared. M's go, M's always go. Multiply by 2. No, not multiply by 2, just add on there. Or subtract, oh, let's just do it right. 2ga on the left, 49 over 2 minus a half is 48 over 2 v squared. And this pops out very nicely. I want v squared, don't I? So that gets me 48 over 2 is 24, 1 over 24 is 12, g over 12 is v squared. V squared is ag over 12. Sorry, v is ag over 12 square root. Okay, so energies. Write down what you're doing. You're only going to have kinetic energy and gravitational potential energy at this point. Occasionally they do make it trickier by saying, okay, well, we're not going to give you at the very top. We might ask you to work it out at this particular point P there. But then you are generally given an angle and you can easily find an expression for that height in terms of cos theta. So all fine, even if you're not given the straight top and bottom. Find the reaction of the ring when the bead is at A. Okay, so nothing too tricky here. Hopefully you'll agree. They have made it particularly nice because we are completely at the top there. So you need to resolve. You always, in the second part, use F equals MA and we are going to be looking at our acceleration being v squared over r, because we've got an expression for v just above. We need to think about forces, however. So, of course, should I draw a bit my circle? There's my circle. There's the ring. The normal reaction going vertically upwards. And, of course, we've got the weight acting down. We resolve in the direction of motion. We always resolve in the direction of motion. So resolve towards the center of the circle. Now, I said the direction of motion. I mean, of course, the direction of the acceleration. Okay, so it is accelerating towards the center. So mg acting towards the center minus r acting away from the center is equal to m v squared over r, little r, the radius of our circle is a. Mg minus r is equal to m times v squared, so that's just the g a over 12, ag over 12, and then I've got that other a underneath as well. Oh, sorry, the a's cancel. So mg minus r is equal to 1/12 mg. So that means that r is mg minus mg over 12. R is equal to 11 mg over 12. Now, that was particularly nice because we were given it at the top, but if we had to work out an expression for the normal reaction, if, say, we were at that point there, I can stop that from happening. What we would do in this instant, okay, we still need to resolve towards the center. That is where our acceleration is acting. We would have r there, but we would have mg acting downwards. Resolving towards the center, you would generally have an angle, don't know, say, it's quite often this angle here, isn't it? But that angle there is the same as that angle there. So you would resolve and you would say that mg cos of theta minus r is equal to ma. So v squared over r, usually you'd get that. So all that it would mean, instead of r just plain old mg acting up there, you would have mg plus some component. I think it's normally the cosine component, but of course it depends on where they define your angle. Okay, so a shorter video. I hope that's okay. I'm not doing any variable forces on this because we have done that fairly recently, so hoping that should be fine with you.